Assuming negligible temperature gradient inside the solid, we could get the temperature profile as a function of time. Now let's see how we can make such assumption. So or when we can use lump capacitance model. Assume that we have a plane wall at Ts1 and it's cooled on both sides by fluid at T infinity. So let's say we have this wall that is initially at temperature Ts1, or the temperature of the wall, not initially, but it is at Ts1 at any time that we are looking. Let's call it Ts1 as a T, and it's being cooled down by fluid on both sides, T infinity, and let's assume at the surface we have temperature Ts2. So let's say this is the surface temperature Ts2, Ts2. And we have the cooling from Ts2 to T infinity on both sides. Inside the solid, let's assume there is a negligible temperature gradient, slight temperature gradient from Ts1 to Ts2. We know that the Q that is coming out of solid, so let's say if there is a Q that is coming out from the solid by conduction, is equal to that Q that is taking out by fluid through convection. So we know Q conduction in solid equal to Q convection in fluid, or in terms of temperature, delta T of the solid, the temperature difference that exists inside the solid, divided by the resistance of solid or conduction, is equal to delta T of fluid, resistance to convection. If I replace here, this is delta Ts. Resistance for the solid is going to be KSA, or let's call it K. We're just dealing with this one solid here. KA is I'm going to just replace delta Ts is Ts1 minus Ts2, and here delta Tf is Ts2 minus T infinity divided by 1 over HA. Now what we want here is a negligible temperature gradient inside solid. What does that mean is Ts1 minus Ts2, we want that to be much smaller than Ts2 minus T infinity. Or if I write it in terms of the ratio, divided by Ts2 minus T infinity, we want to have that to be much smaller than 1. And so if to have a negligible temperature gradient, if you want to have very negligible gradient, we want to have very small thermal resistance too, in terms of the solid. Now, okay, let me just write down first this one first. So the RTH conduction, which is L over Ka, and our convection is 1 over HA. Okay, we want to have this resistance to be much larger than the other one in order to have this this ratio to be satisfactory. In fact, this Ts1 minus Ts2 minus T infinity is, if you write based on the ratio, is going to be L over Ka 1 over HA, or it's going to be HL over K. Okay, and to have this one much smaller than 1, we want to have HL over K to be much smaller than 1. And if we can honor that ratio to be much smaller than 1, then we can say the temperature difference inside the solid is really negligible with respect to what we have outside the solid. And this ratio is what we called Boyett number. So Boyett number BI is HL over K. K is for solid. H is the convection in the fluid. Convection in the fluid that we have. And L is characteristic length. So in general, for L, we write BI is HV over AS, volume of solid divided by surface area of solid divided by K, or we write it based on some parameters called LC. And LC, this is what we call V over AS. That's what we called characteristic length. And that's the ratio of the volume solid divided by the surface area of the solid. Now, if this ratio is much less than 1, or this Boyett number is much less than 1, then the LOM system is valid. So what we have here in terms of the Boyett number, the lumped capacitance approximation is valid or satisfactory. Let's call it satisfactory when we have this Boyett number much smaller than 1, or let's call it 0.1. That's the criteria that we define. We evaluate this Boyett number. If it's less than 1, then we use the LOM approximation. And small V means large K and small h. Okay. In terms of heat flow, what we can say, when you have a large K and a small h, what it means is flow within the object. This solid body that we have is fast, but slow when leaving the object. So inside the object, it is very fast, but when leaving the object by fluid or anything, is very small. A few examples about this characteristic lengths that we have for some geometries. So LC for some geometries. Let's say if we have a parallel wall with the width of 2L for plane wall. Plane wall. We can quickly evaluate that. Let's say we have a plane wall. This is 2L. This is W, and let's say this is length or depth. Let's call it E. Yeah, I use 2L for the width of that. LC is volume divided by the surface area, and volume is going to be 2L WD divided by the surface area is going to be WD plus WD. We have two area exposed to the heat flow. This is one, and there is another one on the other side. So we ended up with L. So LC is going to be L for a plane valve which has a length thickness of 2L. Now for long cylinder, let's say it has a radius of R, or 2R0 as a diameter, and length of H. Then LCV divided by AS would be pi R square H. This is going to give us the volume, 2 pi R0 H. So we're going to get R0 divided by 2. This is going to be the characteristic length for this long cylinder. If you do the calculations for, let's say, cube of each side L, then LC is going to be L divided by 6. And for a sphere with the radius of R0, LC is going to be R0 divided by 3.